Hi, everybody. I hope you had a nice day and are staying safe wherever you are. Um, Today, I would like to talk about what explainable AI is and why do we need this research domain, research field, and what are the challenges in this domain. I would like to give you a little bit of a background about how these techniques work and actually in what projects at AIT we incorporate these methods. But before I start the talk, I wanted to ask you if you know the difference between explanation and interpretation. So I guess I won't be able to see your answers, but the difference between explanation and interpretation is that explanation is just fact that tells us why something happened, and interpretation is basically this particular way that we got to this fact. So remember this because I'm gonna tell you why I pointed this out in the next couple of slides. AI systems, also known as machine learning system, is becoming increasingly present in different domains and applications and becoming increasingly capable of different tasks. But these systems act as a black box and they are missing explainability. What does it mean? That means that these systems are often very much complex and the human expert cannot explain why the system made a specific decision. And that is why the field of interpretable machine learning exists, and this is what we're actually focusing at. This field is also known as explainable artificial intelligence, and is basically a set of iterative processes that goes over time. We get the input, we process the input, do some engineering and analyze the data. We build a predictive model on this input and try to make this model as transparent as possible. What does it mean? It means that we try to look into the model, also the output, to try to justify when does the model fail, when does it succeed, and also why did it make a specific decision, and if we can in general trust the model. So trust is a very generic term. It means that we need to look exactly what the data was learning, and this issue was addressed by Ribeiro in his paper, where he introduced LIME. I'm going to explain it in the next couple of slides. They intentionally trained a classifier which was supposed to say if an image is an image of a husky or a wolf. And the classifier had a high accuracy. When they investigated the feature, they noticed that the classifier actually never learned the features of a husky or a wolf, it just learned the background. So when they looked at the misclassification samples and they noticed that huskies were classified as wolves, it was only because there was snow in the background. And this is an example of a classifier that we do not want to use in critical domains. So back to the explainability and interpretability. Why did I point this out? Because as you notice, I was using these two terms interchangeably because in the community, this is basically a term that is used also interchangeably, but in machine learning community, it is more often interpretability that is used. But in generic term, explainability is basically telling us why something happened, why did the model fail, and interpretability basically focus at the model. So if the model is easily understandable by the human, it's highly interpretable, and if not, then it's less interpretable. Now that we talked about the terminology, I would like to also show you what is out there in industrial awareness. What does it mean? Since 3 or 4 years, there has been a lot of awareness. Why do we need interpretability machine learning? Why does the model need to be transparent? And also the problems when the model is not transparent, because there has been some decisions that have been made in very, very critical domain and nobody could explain it. And there were some people who basically got suffered through those decisions. And that is why there has been an awareness raised, and companies such as Google immediately in 2017 released Google Vizier, which is a platform that you could basically try to make your model as transparent as possible by looking through your model's internal or the outputs of the model and justify them. Then in 2019, there has been a lot of other platforms which have been released, such as IBM, AI OpenScale, such as FICO for Toolkit for credit scoring, and Uber Manifold. And these platforms, some of them are for any general, any domain, and some of them are just focusing for specific domains such as financial and healthcare services or credit scoring. And 2020, of course, there has been more work and research done, but I just want to point out packages which are open source and available for Python, such as Alibi by Sheldon, and such as Interpret ML under a Microsoft license, and also Dalix, which is basically developed by MI2 Data Lab by Warsaw University for R. And there's also another package called IML by Christoph Molnar, and is also used for R programming. So there are so many tools out there now, and they really do try to bring transparency into the algorithm. But how do they work, and why do we need to research further? So the research should not stop here just because we have some tools. And that is why we should look at the studies that are basically done in this field. The interpretability studies are grouped into two. The first one is the model specific, and is through examination of the prediction results by looking at the internal process of algorithms. It can also be part of intrinsic interpretable models by answering the question of how does the model work. There's also the other studies which are model agnostic, and they focus on prediction, interpretation, and justification. So they basically produce explanation of prediction outcomes. And that is why they're model agnostic, because you need to have a trained model with a training data set, and they also call this post-hoc interpretability to tell you, basically to show you what can the model tell us. Each of these studies provide or use different methods. And for model specific, for example, we are talking about intrinsic interpretable models. So these models have to be intrinsically understandable by humans, such as linear regression, where we look at the coefficients of the linear regression. And if you are looking at model-specific approaches, they provide us with feature summary, which is a plot telling us the influence of the features on the prediction outcome. And also we can use target models where we use interpretable models such as decision tree to estimate the decision boundary of a black box model. So these techniques that we are using provide us with two scopes of explanation. They are either global explanation or local. What does it mean exactly? When a technique gives us a global explanation, that means with respect to the train set and the trained model, it tells us what would be the decision of the model for all the outcomes of the unseen data. And for local explanation, we just take one sample and have explanations for that one sample. An example of a global explanation, we have, for example, partial dependence plots, we have accumulated local effect, we have feature interaction, and for local explanations, we have line, we have Shapley values, we have counterfactual explanations, and there are also some approaches which provide us with both scope of explanations, such as feature importance, individual conditional expectation, and SHOP. So I just named 9 different approaches, and because we do not have enough time, I would go through a couple of them which are more popular, such as partial dependence plot, accumulated local effect, and line. So what is a partial dependent plot? A partial dependent plot basically gives us a feature summary and tell us the influence of a feature on the prediction outcome. How does it work? We need to have a trained model. We need to have a training set, and it basically just freezes, and we just have to also determine what is our target feature. So it freezes that target features value for each instance, and then changes the value of other features randomly in order to estimate what is the influence of that target feature on the prediction output. there is a problem with this approach, and that is that it doesn't take the linear interaction of the features into account. And that is why there's another approach called accumulated local effect, where it's very similar to partial dependence, but for each random value that we give to the other features, we have to have a lower and upper boundary, and the value that we choose has to fall into this boundary. And that is why it also takes the linear interaction between the features into account. That doesn't mean that partial dependence plots are not useful. It's just that we need to know when to use partial dependence and when to use A, or what sort of a data set we're using it. And finally, the last method I wanted to talk about is called local interpretable model agnostic explanation, introduced by Marco Ribeiro in 2016. They have a very nice graphic in their website, and I'm going to use that also here to explain how Lime exactly works. So imagine a typical binary classification. We feed a model that can basically distinguish perfectly the difference and what sample belongs to what classes. And then we pick a sample, and that is where Lime comes into the picture. The black line is our black box model, and the yellow dot is the sample that we chose. Now we want to provide an explanation for that one sample. What does it do? Basically, with respect to this point, it gives some weights to the surrounding of this point, and use this weight as the initial weight of another classifier, and fit the classifier to locally explain the decision boundary of the black box. So as you can see here, it can be pretty much accurate because it actually really sees the decision boundary of the black box model. For us in our group at AIT, we need to use these explainability approaches, these interpretability approaches to provide explanations why the model, for example, predicted something, and also when did it fail, why did it fail, how can we actually improve our model. We use it in different projects such as fake unknown shop detection, where we basically look at the internal structure of the code. We use for fake news detection, where basically it tells us what kind of a word in a sentence in a document was the model focusing on to say that this is a fake news or not. I've used it for object detection and automated driving to tell, for example, why did the model detect that this is a specific object, what was the most focus, and why the model says that we need to drive left or right, and also for predictive maintenance. Since my topic is predictive maintenance and I apply explainability on predictive maintenance, I would like to go a little bit deeper and tell you what exactly that is. So a little bit of a background for those of you who do not know what predictive maintenance is. Imagine you have a car and you're driving with your car. After some point, you notice that the car makes weird sounds. And then you just don't pay attention to it because it's working. And after some time, you notice that, okay, I have problems starting the car, but it is still starting sometimes and I can drive with it. And then still you don't go to a service to maintain your car, and then it goes to a failure mode. So this is the point where it's so expensive to fix it. And that is why predictive maintenance comes in. We have something called scheduled maintenance, and this could be very expensive. This could be also cheap, depends on the situation that your car is in. And that is what we are trying to predict. So we want to know exactly when is a good point to apply maintenance on your equipment, on your machine. And what is the benefit? We reduce the unwanted maintenance costs, and also we increase the production. And it's basically all about reducing the cost in the industry. The goal of predictive maintenance is to have a system, a prognostic system, which uses either model-based, where we simulate the equipment, or is data-driven based, which we as data scientists use the data to predict something. And this model should send us an early warning when does the model need maintenance action. There are some tasks that we could basically do in predictive maintenance. And two of the popular one, I'm going to tell you what that is. So there's this period where your machine is healthy, it's running, there's no problem. And then there's this period where your machine makes weird sounds, but it's still in a good, acceptable quality. And then there's this period where it has difficulty to sometimes get started or not. And then, of course, there's this period where nobody wants to go. The one that it's in the failure mode or the breakdown state, we could estimate how long do we have until that point, which is called time to failure estimation. And then there's another one where we could estimate this threshold until when I have an acceptable quality of production, I have an acceptable quality of my machine working normal, which is called remaining useful estimation. How do we solve these two? How do we do this task? We could do either with regression analysis. How long does my machine have until it is still in an acceptable quality, or how long does my machine have until it goes to a breakdown state? We could also do classification, where we say which state is my machine in? What sort of a state? Is it in the healthy, or is it in the breakdown? Is it in the failure mode? And these are the ways that we could solve these two tasks. So how do we apply interpretability into it? We basically have our car, we install some sensors on it to get some data from it. Depending on the equipment we have, we could get different sort of data, such as vibration, voltage, heat, and we analyze the data. We build a predictive model on this data and predict when does the machine go to a failure point. Then we take this trained data, we look at the prediction, and we apply a one of the interpretable techniques on it. This is an example of line, where I looked at why the model says that we are at the failure mode. And what does it tell me? It's basically that at each time step, the value of a specific sensor or other sensor are falling below a specific threshold. So it gives me a range of qualities. And then I have to look at my data and see, okay, so that is actually true. Or my model is actually not as robust as I thought, because, I don't know, it basically is modeling the noises as well. And this is how I use these techniques for predictive maintenance. So to have a summary of the talk today, the goal of this research field is to have as accurate as possible explanations, and also to have easy and comprehensible explanations. They shouldn't be very complicated to understand. And then there are some problems that, for example, they're very subjective and they're very domain specific. We cannot apply some of the techniques in some of the domains. As I said before, we have a little bit of a problem with interpreting time series with the existing approaches, because most of the approaches focus on computer vision, convolutional neural networks, for example, and text analysis. There's also another problem, is that we do not know how to evaluate these systems. How do we say an explanation method is a good explanation method? They roughly group them into three. Either they could be application grounded, where you just take the domain expert to evaluate the systems for you, which is very expensive. Or you could just use normal participants with completely different backgrounds. Or functionality grounded, where you look at the mathematical complexity of those approaches and compare them with each other. These are the references I used for my talk today, and some good reads that I want to point you to. There are many if you want to get into explainability, but I found them very complete and informative. And for predictive maintenance, if you are also interested, you could look at the PHM Society Prognostic Health Management. They have public data sets and many, many publications to introduce you to the field. Thank you very much for your attention, and I'm available for any questions.
Thank you, Anahid, for your talk. We have one question. It's you talked about model-specific and model-agnostic approaches.
Mm-hmm.
Are there attempts to reverse engineer machine learning models to gain information about how they work?
Yes, but that would be also very model specific.
Can you name one example, maybe?
The specific name of the approach doesn't come to my mind, but there are some which they look at the, for example, they create a heat map for neural networks, or they look at the loss function and look at the backpropagation of how these models are trained to be able to explain those models. But I can actually add them into my references, and when you make the slides public, then you could have that with the name as well.
Thank you. We have another question.
Mm-hmm.
You talked about using machine learning for detecting fake news. Does this not bear a big risk to more or less censor different opinions?
Well, actually, this is not my expertise, but so far the results that we are getting are very unclear, because what the model is looking at sometimes it doesn't make any sense. The words that it's highlighting, it doesn't make sense to us, and it's also very, very subjective. What we, for example, for hate speech, what is considered as a hate, and what is considered as a normal evaluation or a normal comment or something. So that is all I can say actually about this at the moment.
Thank you. I think there's somebody writing in the chat. There's another question. Can you give a brief overview about ethics in AI, as this topic is changing regularly?
A brief overview. You need ethics in AI, because if you train a model and you cannot explain what the model is saying, you will end up having cases where you give a person very low credit, and it's maybe because the model was racist, or maybe the model was sexist. And also there are some samples where the model was, again, very sexist, because it was looking at the text where the text was very biased towards a specific gender and made the prediction based on that. So this is why we need to bring a transparency, and this is what we talk about ethics. And that's why the models need to be transparent, to not have this injustice based on the prediction of the model.
Thank you. The slides will be online. Somebody asked in the chat if we can go back in the slides, but you're gonna make the slides public.
Okay.
Okay. We're waiting for questions. What topics would you recommend for a master thesis regarding XAI?
I'm sorry, it's topic for the thesis?
For master thesis.
If you have it at AIT.
I guess.
Okay. Well, not now at least, but there will be definitely some coming, because this is a very, very, it's getting very attention, and it's getting very popular, and there are so many challenges we need to solve.
I think there are no more questions. So reaching the end of the Q&A, I want to thank you very much for your presentation. And
thank you for having me.
For everybody who's watching, you at the end of the talks, you will get an opportunity to have a private talk with Anahid. So stay tuned.